Welcome back. In the previous lecture, we have discussed the correlator type receive filter and its basic architecture. In this lecture, the maximum likelihood deduction using correlator type receiver filter will be discussed, and also the signal to noise ratio will be described. We know that the transmitter is transmitting m number of symbols and this transmitter symbols are corrupted by additive white Gaussian noise. And the received signal will be represented as Si of t plus n of t. So the transmitter vector, symbol vector transmitted is given by Si is equal to Si1, Si2 up to Sin, and all these elements of the vector are added by the additive white Gaussian noise after the correlator receiver. So in the correlator receiver, R of t is multiplied by psi j of t, and it is integrated over a symbol duration Ts, and Ri is evolved. So the received vector can be written as so each of the received element Rij is represented by Sij plus n, where n is the additive white Gaussian noise. So here we are going to estimate or deduct Sij from Rij is taken care by maximum likelihood detector. Since this is an additive white Gaussian noise environment, and the signals or symbols are equally likely and independent to each other. That is, S1 of t, if we are having m number of symbols which is represented by S1 of t, S2 of t up to Sm of t, each of the symbol S1 of t is independent to S2 of t and S2 of t is independent to S3 of t, and likewise we can relate, and each of the symbols are independent. Hence we can determine the maximum likelihood deduction. So the symbol vector Fi is transmitted and it is added by noise, and after the correlator receiver Ri is received. So each of the every element in the vector is corrupted by the noise. That means we are receiving Ri when Si is transmitted. So the conditional probability for receiving Rij when Sij is transmitted then it is given by P of Rij given Sij for I less than or I between 1 to n and 1 to m and j between 1 to n. So the overall conditional probability for receiving a vector R while Si vector Si is transmitted. That is, PR given Si is written as the product of the individual conditional probability for receiving Rij when Sij is transmitted. So the product of j is equal to 1 to n and Prij given Sij. Where I is between 1 to m. So we can receive any vector R during the transmission of ith vector, which is represented by the product of all the probabilities, since the probability for receiving Rij when Sij is given is independent to all other orthonormal basis function. And here Prij given Sij can be written as 1 divided by root 2 pi sigma n square e to the power of minus Rij minus Sij the whole square divided by 2 sigma n square. And we know that the variance of the additive white Gaussian noise is sigma n square is equal to n naught by 2, where n naught is noise power per unit bandwidth. Now, this Prij given Sij can be written as 1 divided by square root of 2 pi n naught by 2 multiplied by e to the power of minus Rij minus Sij the whole square over 2 sigma n square. Sorry, sigma n square can be written as n naught by 2. So here 2 will get cancelled. So P of Rij given Sij is nothing but 1 divided by square root of pi n naught multiplied by e to the power of Rij minus Sij the whole square divided by n naught. Hence, the conditional probability, the overall conditional probability for receiving error vector R is the probability of R given Si can be written as product of j is equal to 1 to n e 1 divided by square root of pi n naught multiplied by e to the power of minus Rij minus Sij the whole square divided by n naught. This can be represented as one divided by square root of pi n naught product of j is equal to 1 to n e to the power of minus Rij minus Sij the whole square divided by n naught. Hence, the log likelihood function can be represented as by the natural logarithm of conditional probability, that is ln of probability of r given Si can be written as natural logarithm of the entire term. Which can be represented as we are having n number of product terms. So during the application of natural logarithm, the multiplication factor will become, the product term will become the sum terms. So n times this 1 divided by square root of pi n naught is added together. We can write n into natural logarithm of 1 divided by square root of pi n naught, and then the sum product will become sum. So summation of I is equal to j is equal to 1 to n ln of e to the power of minus rij minus sij the whole square divided by n naught, which can be written as n into ln of 1 divided by square root of pi n naught, and the natural logarithm of exponential term will become 1 by n naught into summation of j is equal to 1 to n or ij minus sij the whole square. In this log likelihood function, the Hamming distance d can be represented as rij minus sij. For maximum log likelihood function, the log likelihood function should be maximum so that the Hamming distance should be minimum. In order to achieve a maximum log likelihood function, always the Hamming distance should be chosen, or the estimate should be chosen in order to reduce the Hamming distance. Hence, the estimate of Si can be written as argument of maximum in which I from 1 to m the log likelihood function, which can be expanded as Here, if this function should be maximum, the Hamming distance should be minimum. That means we can choose the estimate by considering the minimum argument value within the range of I from 1 to m from the term j, summation of j is equal to 1 to n or ij minus sij the whole square, which is in the form of a minus b the whole square. So it can be written as or ij square plus sij square minus 2 or ij. So here it is represented as argument minimum of from the values I 1 to m summation of 1 to n or ij square minus of 2 or sij minus sij the whole square, sij square. So if this expression to have a minimum value, the second term should have the maximum value. So the estimate can be represented as of minimum 1 to m summation of j is equal to 1 to n 2 or sij minus sij square. Here or sij is the correlation coefficient and this correlation coefficient should have the maximum value and the Hamming distance d should have the minimum value in order to estimate the original signal which is transmitted by the transmitter. So if Rij is equal to Sij, then Si cap will be Sij. So Si cap will be estimated as Si. If Rij is equal to Sij, then we will have a perfect estimate, that is Si cap is equal to Si, but this estimate is attained while receiving Ri given Si. But this possibility cannot occur while the presence of during the presence of additive white Gaussian noise. So the maximum log likelihood function is chosen to maximize the log likelihood function in order to reduce the Hamming distance and to maximize the correlation coefficient to have a good estimate. Let us discuss the signal to noise ratio of the correlator receiver. Assume Fi of t is transmitted by the transmitter which is corrupted by the additive white Gaussian noise N of t and allowed through the correlator filter. And the input is R of t, and let us assume the output as y of t, and this is sampled by the sampler at t is equal to nts, and at the output we will have y of nts. At the input of the correlator, we can determine the SNR input, and at the output of the correlator, we can determine the signal to noise ratio output of the correlator type receiver filter. So the received symbol can be represented as R of t is equal to sum of the transmitted symbol Si of t and the additive white Gaussian noise N of t. So the input signal to noise ratio can be calculated as signal power over noise power. The signal power can be estimated as Si of t square divided by the noise power can be estimated as N of t the whole square. And the output of the correlator receiver is given by y of t is equal to integral of 0 to ts r of t into psi j of t dt, where r of t is nothing but the summation of si of t plus n of t. Hence, the integration can be expanded as integral over ts si of t psi j of t dt plus integral over ts n of t psi j of t dt. The first term is the transmitted symbol term which is transmitted by the transmitter, and the second term is the noise present at the receiver end. So the output signal to noise ratio we can assume this as ys of t plus yn of t. So the output signal to noise ratio of correlator type receive filter can be written as SNR output is written as signal power over noise power, where signal power can be represented as ys of t the whole square divided by expectation of yn of t the whole square. The noise power is calculated by expectation of yn of t the whole square can be written as integral of 0 to ts n of t yn of t into yn conjugate of t dt, which can be represented as the expectation of integral of 0 to ts n of t into psi j of t dt, then integral over ts n of tau n conjugate of tau psi j conjugate of tau d tau, which can be represented as integral of 0 to ts double integration expectation of n of t into n conjugate of tau and psi j of t into psi j conjugate of tau dt d tau. And this is nothing but the autocorrelation of additive white Gaussian noise, so which can be represented as n naught by 2 into del of t minus tau. And this Dirac delta function will only be true for t is equal to tau. Hence, the integral with respect to tau can be removed so that n naught by 2 integral of 0 to ts psi j t the whole square dt, and this is the energy of orthonormal basis function, which is equal to 1 joules. We have already discussed. So the noise energy, the noise power can be represented by n naught by 2. Now let us discuss the signal power at the output of the correlator receiver. Which is given as f ys of t the whole square can be written as integral over 0 to ts si of t into psi j of t dt the whole square. From Cauchy's quartz inequality theorem, integral of u of t v of t dt the whole square will always be less than integral of u square of t dt multiplied with integral of v square of t dt, and this should always be less and not equal, and this expression will get equal, that is equality is attained when v of t is directly proportional to u of t. That means v of t is equal to c into u of t, where c is a proportionality constant. So if we apply this in the signal power, then ys of t the whole square will always be less than or equal to integral over ts si of t the whole square dt into integral over ts psi j t square dt. And we know that this is 1 joules and this is the energy in the ith symbol, energy of the ith symbol. Hence, the output signal to noise ratio is given by is less than or equal to, the numerator is EI and the denominator is N0 by 2. That is, the signal power is always less than or equal to EI and the noise power is N0 by 2. So SNR output will always be less than 2 EI by N0, where EI is the symbol energy over a time period of Ts, and where Ts is the symbol duration and N0 is the noise power per unit bandwidth. So this inequality will get equality, that is the maximum value of the SNR is bounded by 2 EI by N0, and that is maximum value of SNR of 0, SNR output is 2 EI by N0 is only attained when psi j of t is always proportional to si of t, that is psi j of t is equal to c si of t, which is not possible because any ith symbol is an algebraic sum of n number of orthonormal basis function and it is independent to each other, and each orthonormal basis function are orthogonal to each other. Hence, this condition cannot be achieved with the help of correlator type receiver filter, so that the maximum SNR cannot be attained while using the correlator type receive filter in the presence of additive white Gaussian noise channel. Hence, we are in need of another type of receive filter, which is used to optimally receive the signal or receive the symbol by attaining maximum signal to noise ratio. And that filter is called as matched filter, which will be discussed in the next session.